what happens if you have non-conservative forces in a simple harmonic oscillator? For example, if you have friction on a simple harmonic oscillator, or if you have wind resistance. Think about a child swinging on a swinging on a swing. That child, as they swing back and forth, encounters air resistance as they move through the air. There's some friction at the top where the chain links up with the top of the swing. Those forces together act to dampen the motion. What do I mean by dampen? Dampen means to reduce in intensity. So damped harmonic motion, if you look at the amplitude or the position, x here, the displacement, as a function of time, you can see that in dampened motion, the period stays the same for these oscillations, but the amplitude changes. When the swing or the block, if it's on a friction surface, tries to come back to its maximum displacement, it doesn't get there, right? So what happens is work is being done by a non-conservative force that changes the total kinetic energy and potential energy. We talked in the last video how the maximum energy of the system was equal to 1/2 the spring constant times the amplitude squared. But if you sap energy from the system into thermal energy, like through friction or through air resistance, then the total energy has to change. Well, the spring constant, K, isn't changing. That's a function of the spring. How stiff is the spring? That doesn't change with time for this oscillator. So the only thing that can change is the amplitude. As the total energy gets smaller, the amplitude gets smaller. So if there are no non-conservative forces, the change in kinetic energy plus potential energy is 0, and that thing will oscillate forever, always going back to the same amplitude. If there are non-conservative forces, work is being done, usually in the form of friction, to slow an object down, and you end up with dampened motion. Again, a child on a swing, assuming they're not actively pumping, as they swing, the swing gets lower and lower and lower and eventually stops. This is dampened motion. Now, sometimes this is good and sometimes this is bad, right? Dampened motion is bad for a swing, you can think of, because if you get enough energy, get a push, you want to keep on swinging. You don't have to keep on working every time you want to continue to swing. But sometimes dampening is a good thing. For example, the shock system in your cars. The old cars especially, that would have the old metal large shock absorbers, the large springs. When you go over a pothole or when you hit a rock with your car suspension tries to address that change, right? You have 4 wheels of your car on the ground. If one of those goes in a pothole, if your car's wheels were firmly attached to the frame and everything, there were no springs, there was no suspension system, your car would drop in that direction rather abruptly. That's very uncomfortable. If you've ever driven a car without suspension or reduced suspension over a bumpy road, you can feel every bump in the road. When we're driving down the highway or driving down the city streets, we like a smooth ride, right? That's one of the nice things about the luxury vehicles is how smooth and quiet they are as you're inside. But they still encounter potholes. They still encounter rocks in the road. How do they deal with it? Well, they place spring systems, elastic systems in the tire, so when the tire goes over a rock, the tire raises up. Or if the tire hits a pothole, the tire can drop down. That, if you think of it like a spring with a tire at the end, if you go in a pothole, the tire drops down, that will start oscillatory motion in your front tire. You don't want that either. You don't want the car bouncing down the road. So what you do is you set up a dampened system. So when the car's tire does, when the spring is compressed as it goes over a rock, or it's stretched out as it goes in a pothole, the car's wheel quickly goes back to the equilibrium position and doesn't oscillate about the equilibrium position. So that's called critical dampening. Critical damping occurs when, after a deviation, it quickly goes back to the equilibrium position. Another wonderful example of that is buildings. Imagine a tall building, as the wind hits it, that building can start to sway. That's bad for a building. Most tall buildings have in it the ability to do at least some motion. But you want to set up, usually a counterweight system, that undoes that oscillation. You want the building at the equilibrium position, stationary and upright. You don't want it rocking about the equilibrium position. So they put in dampeners to prevent that from happening. Now, that's critical dampening, is basically dampening that brings the system to equilibrium position as quickly as possible. You can have an underdamped system or an overdamped system. The underdamped system, the example that probably works best is old cars with their old spring suspension. You can kind of tell when the suspension system needed replacing. You put your foot on the bumper and you push down on the bumper and let your car start to bounce. And if your car didn't quickly come to the equilibrium position and stay at rest, if your car continued to bounce for a while, it was underdamped and you needed to replace the system. Overdampening basically means that the oscillation motion is killed too quickly to go back to equilibrium. So for example, imagine a tire. Here's a tire going over a rock. Let's draw it out. We have some tire attached to a spring attached to the frame of your car. There's a rock here, so when that tire hits the rock, right, the spring is compressed even more than it already is. That starts in, so the displacement is upwards, so the force for the spring is trying to push that tire back down. But in an overdamped system, the oscillations are killed so quickly that the tire very slowly descends back to the equilibrium position. An example of an overdamped system is a swinging door that has the hydraulic system on the top. So when you open the door doesn't just immediately slam closed, but it very slowly closes. That is an example of an overdamped system. There is a spring trying to close the door, but there's a hydraulic system in there to make sure that happens slowly, so the door doesn't slam. That is an overdamped system.